This lecture is planned to discuss application of chemical ensemble formalism. So by now we are familiar with partition function in the chemical ensemble formalism. So we write partition function using symbol say Q or using symbol say Z. So it is nothing but sum of Boltzmann weight over energy value ER for all possible R. So ER is the energy which your system is occupying at temperature T. This beta is inverse temperature, that is 1 upon kT. So ER divided by kT is some number. Exponential weight of it will give you, with minus sign will give you probability of finding that energy state, and summing over all possible R, all possible states, energy state will give you partition function. So with this partition function Q in chemical ensemble formalism, you can write your Helmholtz energy, that is nothing but minus kT log of that partition function. So from there you can determine entropy of your system, you can determine pressure of your system, you can determine chemical potential, you can have a specific constant volume, you can have useful energy, right? So in order to appreciate this approach, you would like to see application of this chemical ensemble formalism using a problem of quantum mechanical harmonic oscillator. So in the case of quantized harmonic oscillator, we can write energy of oscillator using this expression En, that is n plus half h cut omega. Then n is 0, your energy of oscillator is 0 point energy, that is half h cut omega, and 1 3 by 2 h cut omega, and so on. So with the increase of n, your energy of the oscillator will increase. So you have n number of such oscillator which are allowed to have energy varying according to this relation E small n, occupying volume say capital P, and these oscillators are kept in contact with the heat reservoir to maintain temperature say capital T fixed. So beta is inverse temperature. So we have partition function of a single oscillator Q1 beta, which is function of temperature. It is nothing but sum of Boltzmann weight of this oscillator for all possible value of energy state which is accessible to your oscillator. Okay, e power minus beta En is given here. So you are substituting possible values of n which is ranging from say 0 to infinity. So your first term is e power minus beta half h cut omega. Second term e power minus 3 by 2 beta h cut omega. Third term e power minus 5 by 2 beta h cut omega, and so on. So this is an infinite series. E power minus beta h cut omega is less than 1, then only you can sum this series. Okay, you are in the quantum regime, so your energy of oscillator h cut omega is dominant than thermal energy. So in that situation you are in the quantum regime, that's why you have some of this series that can be written in this fashion. So that is nothing but e power minus beta half h cut omega upon 1 minus e power minus beta h cut omega. So we can divide numerator as well as denominator of this single particle partition function with e power minus beta half h cut omega. So in the numerator you have 1, in the denominator you have e power beta h cut omega upon 2, here e power minus beta h cut omega upon 2. So this term is nothing but 2 sin hyperbolic beta h cut omega upon 2. So we have Q1 beta, that is 2 sin hyperbolic beta omega dash. Omega dash is omega upon 2. For the sake of mathematical simplicity, we replaced omega dash, that is omega upon 2. So we don't need to write by 2 all time here. So Q and so this is the single oscillator partition function at T temperature. Similarly, you have n oscillators, each oscillators are independent to each other. That's why you can write Q and beta, that is single particle partition function power n. So you can write free energy, Helmholtz free energy, that is minus kT log of Qn. So minus sign is there, so minus it will give you plus. So A equal to n kT log of 2 sin hyperbolic beta h cut omega dash. Omega dash is basically omega by 2. So from there you can determine pressure, chemical potential, entropy, specificate it constant volume as well as constant pressure. You can determine energy of your oscillator. So this time students are supposed to determine their own expression is known to you, so you can take derivative with respect to V, N, T and so on to determine all these parameters. Now we move to another ensemble theory, that is grand canonical ensemble theory, that is generalized ensemble theory. Generalized ensemble theory of canonical ensemble approach. So in the case of grand canonical ensemble theory, we have system defined using three thermodynamical parameters. One is chemical potential, another one is volume of the system, and T is temperature at which your system is kept to have fixed value. So these are the three parameters. In this case, your partition function, that is grand canonical partition function, you can write like this: mu power n, mu is chemical potential, power n, q and vt. This q and vt is a fixed particle partition function or canonical partition function of your system, where system is defined as n, v and a t. You have n particle, number is known to you, and mu power n, you are summing this term mu power n, q and vt for all possible n, which is running from 0 to infinity. So it will give you grand canonical partition function. Your system is defined using mu vt. There is no restriction on to the number capital N. So once you have grand canonical partition function that you can determine, you can write free energy, Helmholtz free energy according to this relation. This is the grand canonical ensemble approach. So Helmholtz free energy, in this case you have G mu vt upon mu power n, right? So from there you can determine entropy, you can determine pressure, chemical potential, internal energy or energy of your system, specific heat, gives energy, and a number of particles or number of oscillators in your system. So detailed approach one can see in detailed approach of this grand canonical ensemble theory one can see through my lectures and the material which I have circulated to students. So this completes your ensemble theory.